Next, I'd like to talk about a concept that we like to call like terms. Like terms are terms that we can add and subtract together. What makes terms to be alike if they have the same combination of variables attached to them. So we've been doing like terms all the time. Constants are like terms. So 7 minus 4. These have the same combination of variables, specifically none. So we can add them together or subtract them together to get to 3. 7x minus 4. I can't really combine these together. If I could combine these, then that would be violating the order of operations, because that's like saying that I can do subtraction between these two numbers before the multiplication of this known number and this secret number. Since we don't know what the secret number is, we can't resolve the multiplication, which means we're kind of stuck. So we can't combine these. These are not like terms. So this expression kind of sits there. Once we have an equation, and this can equal 3, I guess. I mean, this is a two-step problem at this point. You just add 4 to both sides, break apart the weakest bond, and then divide both sides by 7 for x to equal 1. But that's not what I'm talking about here. That's something we can do in an equation. What about if I have this expression here? One could argue that since we still don't know what these secret numbers are, we can't do the multiplication, and then therefore we can't do the subtraction. But let me prove to you that we can combine these two terms. What if I were to, I'm not going to go into this concept called factoring, that's later on, which is basically going backwards through the distributive property. Cover your hand over that expression for a second. And let's say I had just this problem for you to do. I say, okay, distribute this. Okay, x times 7, x times 4, and we keep the subtraction. Oh, hey, look, there it is. That's all factoring is we're kind of like pulling out the common factors between them and then turning it into a distributive property problem. That still doesn't prove that we can combine them. But what we can do is, instead of distributive property, we can combine 7 and 4 like this. 7 minus 4 is 3, and then 3 times x is 3x. Okay, well, if all of these are equal to each other, if this is equal to this, and this is equal to this, then by something called the transitive property, meaning if, like, A is equal to B and B is equal to C, then naturally that first thing is equal to the last thing. Therefore, this has to be a true statement here. Well, what did we do? We subtracted the constants, just like if it was just 7 minus 4, we did 7 minus 4 is 3, and then we kept the variables. This is what it means to combine like terms. If you have 2 or more terms with the same combination of variables, you can add them and subtract them, but that, like, sum or difference at the end has to have those variables as well. So it's like I have 7 x's and I got rid of 4 x's. How many x's do I have left? Yeah, here's something that can be confusing. 5x squared plus 3x squared. They have the same combination of variables. They both are x squared terms. So indeed, these are like terms. We can add them up. So this will be 8x squareds. Now, what if I had 5x squared plus just 3x? Well, they both have x's in them, but it's not the same amount of x's being multiplied together. This one only has one of the x's. This one has 2. So these are not like terms, even though they kind of look like it because they both have the same type of variable. It's not the same combination of variables. And very quickly to kind of prove it, exponents happen first, at least, before any multiplication or addition. So in this expression, exponents would happen first. So we would square the x, then we can do the multiplications. But saying that we can do the multiplications or even the additions before the exponent, again, violates order of operations. So this is the same thing as, I'll bring it back up here. Same thing as this. It's saying we have to do some sort of higher order of higher tier in the order of operations before we can, we have to do that before, yeah, you get what I'm saying. We can have more than just a single variable. We can have multiple unknowns. These are like terms because they have the same combination of variables. What about if I used the commutative property and just switched the y and the x? Are these still like terms? Yeah, they are. But there's a general convention. When it comes to the letters that we choose for the variables, we write them in alphabetical order, just so everyone knows how to kind of organize these multivariable terms, because since multiplication is commutative, we can organize them any way we want, so why not just do something that's familiar to us, which is the alphabet. So this would be 7xy. So this leads us to two-step problems in which variables are on both sides. Doing 100 two-step problems where you only had one variable term, it's natural to think move the 2 to the other side. But if you can see here, that didn't really accomplish anything. Nothing combined. Yes, it's a legal move. We always want our moves to accomplish something. So the better thing to do is to get all of the variable terms on one side and then all of the constant terms on the other side. That still hasn't changed, but here we have to actually combine variable terms. We have to move 5x. So there's only constants on this side now. We have to do the property of equality properly, which is this. Then we have 2 equals, those cancel, 3x minus 5x is going to be negative 2x. Then we divide both sides by negative 2 to get the variable by itself. So we have x equals negative 1. Two-step problem with multiple variable terms. They're like terms, therefore we can combine them using our like terms thing.